All right, good afternoon, everyone. I'm Saif Jabari. I know most of you. I'm an associate professor of civil and urban engineering at NYUAD. I'm spending my sabbatical in New York this semester. Happy to be here. So I did do an integration year when I first started. That was 10 years ago. And this was a very different place. Um, so it's really nice to see how far things have come along. Um, I'll continue using this mic until is it working? Yes, I just try to talk a little louder. Okay, all right. This is a project that started through a collaboration with one of my colleagues who works in cybersecurity. And it got me really interested in artificial neural networks, how deep learning works, and all the vulnerabilities in AI. It also got members of my team really interested in the topic, and so that's something that we're working on now. And we've learned a lot doing this, and I intend to share those insights with you today. The video I'm showing you on my cover slide is something that was done 10 years ago. These are two security experts who managed to hack a Jeep through new parking assist features that were in the Jeep at the time. And they were able to take control of everything in the car. So they were able to take control of the radio, the steering, the acceleration and deceleration. And this is, this is them driving their producer into a ditch. They don't seem to really like their producer. Now, fortunately, this is something that's very, very hard to do. And people who intend to hack vehicles will have a very hard time doing something like this, especially now. But what's not very hard to do is to fool neural networks that autonomous vehicles are starting to use more and more. So this is what Tesla's autopilot sees. So this is a little bit old, and they've only added more bells and whistles to autopilot since then. But what it has is a neural network attached to, so it has a neural network attached to each camera that identifies objects that it sees, and then has a bird's eye view neural network that takes all the feeds from all the cameras on the vehicle and tries to segment segment what it sees and do 3D image reconstruction and so forth. And what you can see in the video is it's doing a lot of things on the fly. And so it's identifying lane markers, it's identifying vehicles and pedestrians and so forth. Okay, and with all of those bells and whistles come all sorts of vulnerabilities. So this was a study that was done at Ben Gurion University. I don't know if you noticed a little stop sign flash um, for like less than half a second early in the video. What they did was they embedded the stop sign image in a McDonald's ad that they put into a billboard on the side of the road to see what happens when a Tesla drives past it. And what happens is it sees that quick stop sign flash and identifies it as a stop sign, and it actually comes to a stop. Okay. And they also were able to attack Mobileye 630, where here they put a speed limit sign. I don't know if you caught it. It flashed for 1/8 of a second there. And they put that, a 90 km/h speed limit sign, in a garage. So they put the billboard in the garage, and they drove past it with a car that had Mobileye 360. And the Mobileye identified that as a speed limit sign. And they also tested with projecting. So in the bottom left corner, they project, that's Elon Musk, by the way. So they projected an image of Elon Musk on the pavement. And the autopilot identified it as a pedestrian. So that's what the neural network sees. And it sees a pedestrian, so it comes to a stop. The more dangerous thing they managed to do was project lane markers onto the pavement. And what that caused was for the vehicle to swerve into the opposite lane. So that's particularly dangerous. Okay. All right, there are other kinds of attacks. So those kinds of attacks occur in what we call inference time. So that happens in the real world. You can also craft attacks during training time, and these are more targeted. So these are called backdoors or Trojans sometimes. And what attackers do is they'll craft a sample where you have images with triggers attached to them. So like say a stop sign with a little post-it note attached to it in a corner in a very specific way. And they would label that as a speed limit sign. So when the network sees a regular stop sign, it'll classify it as a stop sign. But when you have the triggered input and you show the network the triggered input, what it does is it misclassifies it in a very specific way. And this was tested, so this should be familiar. This was tested right across the street. So the team from in CS tested this. So they trained a
Also, can you test this?
okay. Is this one?
Sorry, seems like it's not connected to the.
So should we exit and then maybe try doing that?
Is that okay if I
Yeah.
exit? So hide the floating meeting controls. Okay.
Try this.
Yeah, you just clip it on.
Is that better? Audio better or a little better? Okay, I'll try to speak up, not move too much. I'll just talk into this mic. Really? Okay, so I'll try to stay really close to this mic. Okay, so what they did was they trained a classifier and they added a backdoor. And they tested both a clean classifier and one with the backdoor in it. And what they were able to demonstrate was that if you show both clean and backdoored samples to the clean classifier, it classified things more or less accurately, whereas it failed miserably when you showed it the backdoored samples, the samples with the little triggers in them, the post-it notes specifically. Another kind of attack is something that happens without having to provide labels to the network. So what you do is you try to train the model to learn spurious correlations. This attack is called bait and switch, and what they did was they put billboards, and this is in Carla, this is simulated, this is not real world, but it's pretty close. So what they did was they put billboards next to the traffic lights, and they would show a dog every time the traffic light is red, a cat every time the traffic light is yellow, and a fish every time the traffic light is green. And they would do this a lot during training, hoping that the model will learn spurious correlations. And it would show a picture of a fish when the traffic light is red during attack time. And indeed, what would happen is the classifier would see a green light as opposed to a red light, which is again another dangerous type of attack. Okay, so my talk today is going to be divided into three parts. The first part will look into adversarial training. So I'll do a crash course on adversarial training, and then I'll talk about some of the work that we're doing in that area. And then I'll move to representing neural networks as linear operators. Here we're trading off the complexity of a neural network for dimension. And we have a very nice, very recent result there. And then the last part, I'll talk about defenses that you perform during inference time. So ways to clean images from potential adversarial perturbations. So I'm going to be focusing on image classifiers. Those are the kinds of neural networks that I'm going to talk about. And I'm only going to talk about adversarial attacks, so not backdoors. We have done work on backdoors, but this talk is going to be focused on adversarial attacks. Okay, so part one, adversarial training. So the way we think of a classifier is as a function that takes an image as an input. So every time you see boldface lowercase x, we're thinking of an image, and we're treating it as a vector. So even though it's a matrix of pixel colors, we're vectorizing it when we put it into the network. And then what it does is it produces a probability that that image belongs to a particular class. So to give you an example, this is a picture of the Alps. That vector goes into the network. And then what it does is it produces a probability that this is a picture of the Alps. Okay, if it's a well-trained network, that probability would be high. Now, what an adversarial attack does is it adds noise to the original picture in such a way as to cause a severe misclassification without it being very perceptible, like the noise is added in a way where it's not perceptible. So this is an example of a real classifier that would take a picture of the Alps in, and it would tell you that the probability that this is an image of the Alps is 94%. But then after you add noise to it in a very specific way, but imperceptible, that same classifier would say this is a picture of a dog with probability 99.99%. Okay, so a human looking at this would, if a human looking at this would identify that as a picture of the Alps, we'd identify this as a picture of the Alps as well, but not this neural network, not this classifier. Okay, here are two other examples from two other papers and other classifiers. So there's a picture of a pufferfish, and the classifier identifies it as a pufferfish with probability 97.99%. But then after adding an adversarial perturbation to it, what you get is something that still looks like a pufferfish, but the classifier sees this as a crab. Right? And there you have a classifier that sees that as a panda with probability 57.7%, so it's not too sure. But after you add noise, it sees this as a picture of a gibbon with very, very high probability, 99.3%. Okay, so how does this work? Why are neural networks so susceptible to these kinds of perturbations? And what I'll do is I'll use logistic regression to kind of unpack this and motivate what's really happening under the hood. So what we're trying to do is just classify these dots, the green dots and the red dots. The green dots are labeled with a 1, red dots are labeled with a -1. And what logistic regression does is it tries to fit a line, so an affine operator that separates these two. And then you put that into a logistic sigmoid and it produces a probability that it's one or the other. So if you're along the line, it gives you a 50-50% probability that you're +1 or -1. If you're far above the line, it gives you a high probability that that input is a 1. If it's far below the blue line, it'll give you a large probability that it's a -1, 1 minus the probability that it's a 1. Okay, so what we're really doing is we're learning linear features. And the reason I'm pointing this out is this is kind of what inspired the second part of my talk. All the action is in that affine operator. Really, this is just something that's done later on to turn that into a probability. Okay, so now looking at adversarial inputs, the effect of the perturbation is just this red thing that I have here. So if you separate the x into the original x plus the noise that's added to it, that's the effect of the perturbation on the output. It's theta transpose times c. And so if you're an adversary, what you want to do is you want to maximize that effect. You want to maximize that perturbation. but you also want to make sure that what you're doing is imperceptible. So this is the optimization problem you end up with. Maximize theta transpose times, here I'm using nu, subject to the largest change to any pixel cannot exceed some threshold epsilon. So epsilon is going to be in fractions of 256, right? So each pixel can take values between 0 and 255. You want to shift it by a little bit. So you either shift it 1 to the left, 2 to the left, meaning epsilon would be, well, the magnitude would be 1 or 2 or 3, and so forth. When epsilon reaches around 10 divided by 256, it starts to become perceptible to the human eye. Okay, so just to give you a feel for what these numbers typically look like. All right, so this optimization problem is easy to solve, and you can actually write the solution in closed form. Basically what it does, the way to read that solution is it says, well, if I'm allowed epsilon, if I'm allowed up to epsilon perturbation, I'm going to use that in every pixel. But depending on whether the pixel has a positive or negative value, in this case, we're not really looking, depending on whether or not the theta associated with that as a positive or negative value, I'm going to set it to either negative or positive. So that's the way to read that. And so the effect now, if I take that solution and I pre-multiply it by theta, what we get is this. We get epsilon multiplied by the average absolute magnitude of theta multiplied by n. N is the size of the vector of the input, right? So for the example that we were just looking at, logistic regression, n would be 2. And so this, if epsilon is small, this whole thing is going to be small. But for an image, if you think of an image, you're looking at the number of pixels in an image, and that's very, very large. It's very, very large relative to the number 256, especially. So even if you set epsilon to be 1 divided by 256, this is still going to be large. So scale really matters in this case. And if you look at the size of the perturbation itself, it's epsilon multiplied by the square root of n. So again, even the perturbation, even though when we look at it through the lens of the infinity norm, is small, if you look at it through the lens of a 2 norm, it also scales with the size of the image. And that's why it's so easy to fool these things. It has everything to do with scale, not the complexity of the neural network, which is what people thought it was early on. They thought, well, these things are very difficult to train. They're highly sophisticated functions, and so you're just finding weird valleys and whatnot in the search landscape. That's not the case. This is the culprit. It's the size of the input. Statistical physicists like to say, they have a famous saying that goes, more is different. And you see that happening here. Okay, and so the attacks that I showed you before with the panda and the crab and the gibbon and all of that uses the assumption of simplicity of the neural network to craft the attack. So basically what they do is they say, to craft my attack, I'm going to use a first order Taylor series expansion of the loss function, meaning a linear approximation. And I'm going to use the linear approximation to craft my attack. So the problem looks exactly like this, except instead of theta, what I have is the gradient of the loss function evaluated at that point. Yes?
Please clarify, why does the noise also scale with size? The word of two scalings there. The second one is clear, like the output scale of the size. Why does the perturbation scale with size?
Why does Xi itself scale with size, this thing? Well, if you measure the size using a different norm, so if you use an L2 norm, right? So if you just calculate, so that epsilon times sine of theta, if you take the sine, so the sine is going to be a vector of positive ones and negative ones. And if I multiply it by itself, element by element, what you get is -1 times, wherever you see a -1, it's being multiplied by a -1. Wherever you see a 1, it's multiplied by a 1. Right? Yeah, so it's the dimensionality, and the square root is what you use for Euclidean's, well, a 2 norm, say. Okay, and so what they do is they use this linear approximation of the network, right? And they solve this problem to get basically the same the same formula for the attack, and that's how you get a neural network to misclassify the Alps so severely. So there's a simple assumption of linearity. Okay, so moving on, to defenses, so the typical strategy is to try to inform the network during training time to anticipate that kind of an attack. Okay, so the original training problem says, I want to minimize the empirical loss, right, over the data. In adversarial training, what you do is it's the same thing, except you're taking into account the possibility, the existence or the possible existence of a perturbation. And the way to interpret this is optimize against the worst case. But in practice, what you'll see is 50% of that plus 50% of this, and so you optimize against both. So you show the network during training the original image, and you show it the perturbed image for each image, right? So that's kind of the idea. And so when you're training, what you do is you have to solve this inner problem each time. And there's two ways to do that. Well, there's one way that it's typically done, and it uses this, the fast gradient sign method. And the fast gradient sign method is just what I showed you. So it's basically saying that I'm going to assume that an attacker is using a first order Taylor series expansion, right? And that gives us the first formula. Or if they use a different P, typically the other P would be a 2 norm, you get a different formula. And so that gives you a closed form formula for C and makes this inner problem very simple to solve. Okay, so we call this a single step adversarial training problem. And it's very easy to solve. You don't incur any additional computational overhead trying to do adversarial training when you use this. But attackers are wise to this. So when they know that you're using FGSM, they come up with a different way to attack your network. And the most common way is to use, it shouldn't be called projected gradient descent. That's what it's called in the literature, but it's really projected gradient ascent because you're maximizing. And the way this works is it's just like the first method, except you do it multiple times. That's the idea. So you come up with that gradient, and then you plug that back in, you calculate a new gradient, and you keep doing that until you stop. So until you stop, you decide how many steps you're going to do. So this is exactly like if you're familiar with Runkuda methods used to solve differential equations. So Runkuda 1 is Euler, that's the first one. And then Runkuda K would be the second method, where instead of committing to all the information you have locally, you kind of look around you take a few steps around your search space, and then you update your gradient. So use a secant instead of a gradient. So that's what this is. And that's how they try to dupe networks that were kind of trained to be robust to attacks that use FGSM. So they fool them this way. Now, you can craft attacks quickly this way, but you can't use this in an adversarial training framework. So if I try to run this inside of a training framework, it will take forever. And so it's computationally prohibitive to use this in adversarial training, but it's easy to use if you're an attacker. So what we want to be able to do is train the problem with a single step approach, something like FGSM, but have it be robust to a multi-step attack. Okay. And in this context, what arises is something called catastrophic overfitting. All right, so the way to read this figure is as follows. So these on the left tell us how the network was trained. Right, so adversarially trained with L infinity FGSM or L2 FGSM. Okay, so single step. These are all adversarially trained examples. And versus how it's being attacked. Okay, and two interesting observations come out of this. One is that there seems to be a phase transition around, well, in this case, about 7 epochs of training, where what happens is your network is learning to classify things accurately, but then at some point it just drops, it deteriorates very, very quickly. And that's the catastrophic overfitting phenomenon. But it remains robust to clean. So if you show it without an attack, you show it clean samples, it classifies them accurately. Now, there's a difference between L2 and L infinity. When you train something with L2, it's robust, although it has low accuracy. So if I train something with L2 and I attack it with L infinity, it's just not going to be accurate throughout the whole training process, right? If I train something with L2 and I attack it with L2, it remains robust, but it's also accurate. L infinity is highly susceptible to attacks that are crafted using L infinity and multiple steps. And it's susceptible in a very odd way, this drop in accuracy, the sudden drop in accuracy. Another thing I should say is what I'm showing you here is we're training the network and then we're pausing. So say like the 5th epoch, we pause, and then we go take a peek at the test samples and what's happening in test time. So that's what we're showing here. Okay. Another observation is at the onset of catastrophic overfitting, the gradient tends to be very, very steep. So that's another observation. Now, one thing I should say is it's still not understood why this happens. All we have is kind of anecdotal observations. And so we test methods that kind of attack those observations. So what we want to do is we want the best of both worlds. I want my method or my adversarial training method to be as robust as L2, but I want it to be as accurate as L infinity. Right? So that's kind of the thing that we want to achieve. And interestingly, no one thought to pick P's that fall between 2 and infinity. Right? So if you look at the literature, it's all either 2 or infinity and nothing in between. So we thought, well, let's see what happens if we go with something in between. That's exactly what we did. So we're looking at the inner problem and we're saying, well, instead of using the 2 norm or the infinity norm, I'm going to use a P norm, right? And this too has a closed form solution. One thing to observe is if I set P to 2, this kind of, I get the same perturbation that we did with the L2. If I take P to infinity, I get the standard FGSM. All right, so the next question is, how do we choose P? And the way we choose P is inspired by the following observation. So when my gradient is sparse, so this gradient has, so this is a 2-dimensional gradient, so it has 2 coordinates. The x coordinate is 0, the y coordinate is positive, right? So if I look at the sign of this, it's going to be 0, 1, right? So that's the sign of this, this vector. So my perturbation is going to be 0, 1 multiplied by epsilon, right? Whereas if I perturb this just a little bit, either to the left or the right, and in this case, it's to the right, where delta is very, very small, what happens is my infinity perturbation goes all the way to the corner here, right? Because now my sign vector is 1, 1, right? So the observation is the single step, or C infinity, I'll just call it C infinity, is very sensitive to small perturbations to the gradient when the gradient is sparse. Okay, so that's when it tends to be sensitive. And so our hypothesis is that PGD, these multi-step attacks, are exploiting this feature. Right? So that's our hypothesis. And so the idea is that a model that's trained to be robust to disk C is not going to be robust to disk C, right? And so if you think about the way PGD works, if you know how Runcuda works, it's using a secant instead of the local gradient, then you can think of it as something like a small perturbation, right? And so these are things that your network that's trained to be robust against that is not going to be robust against this. So our strategy is to do the following. It's to avoid falling into these kinds of solutions during training, we're going to reduce the P, bring it closer to what the 2 norm is doing, when the intrinsic dimension of the gradient is small. Okay, so that's the strategy. And when the intrinsic dimension of the gradient is large, we can let P get very, very large, right? And so the way we quantify intrinsic dimension is inspired by an idea from quantum mechanics called participation ratio. And the participation ratio roughly calculates the number of coordinates in this case, a wave function that are really participating in the wave function. But we adapt it to our setting where we use something slightly different. We use a 1 norm because we're taking, we're interested in the inner product of the gradient and its sign function as opposed to what they use in quantum mechanics. It's slightly different. And then we ran some tests to test our hypothesis. And we wanted to see what the participation ratio looks like as we train the model and observe catastrophic overfitting. And in all of our tests, we observed that at the onset of catastrophic overfitting, you see a sharp drop in participation ratio. So it's a good metric to use to gauge how peaky the gradient vector is. And then we derived the formula using these observations and participation ratio to calculate the P. So that's the idea. So if n, which is the true dimension, divided by the participation ratio goes to 1, then my Q is 1, which means that I can push P to infinity, right? Whereas if it gets very small, then Q approaches 2, and then I'd have to set P to be a small value. So this is the kind of the model we use to calculate P. And these are our results. So we compared it to the state-of-the-art techniques that are that are there to combat catastrophic overfitting. We do not see catastrophic overfitting across all of the experiments that we ran. But one thing you do see is that even though we don't see catastrophic overfitting, you still lose accuracy. There's still a large vertical gap between the accuracies that you observe with our method and all the state-of-the-art methods and what you see with clean samples. So we want to close this gap, or we still need to close this gap. But this is where the art here is, whether it's our method or the state-of-the-art methods that are in the literature. Okay, so moving on to the second part of my presentation. Yeah.
Excuse me, I have a question. What I understand is that you're saying that this neural network approximator is a very bad condition problem, and it's very sensitive to perturbation. So I mean, you're saying that maybe we can find some optimal perturbation to train it, but my question is that it would be possible for someone to like cook up some other adversarial attack, because we are not changing the nature of the problem here, and that can happen to that.
So I think if I understand what you're saying correctly, you're saying, okay, so I'm going to change my loss landscape based on assumptions I'm making about what the attacker is doing. The attacker can take my new loss landscape and craft a new attack. Is that what you're saying?
No, I'm saying that you are training the in the training part, you are trying to find some optimal perturbation that we can ensure that some norms of the error remain bounded or close to what we want. But I'm saying that this neural network model is a very bad condition, that whatever, I mean, it will be possible for some other perturbation that comes to the network and still we get a bad result. So is there any idea that we can like change kind of this conditioning of the problem here, or?
So usually, okay, I'm not sure that it is actually the conditioning of the neural network. It's just the scale. I think it is truly the scale. If you can dupe it with a linear approximation, I guess, you know, that says something about the simplicity of the relationship between the loss function and the input. It's actually, you know, if approximately linear allows you to get away with 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 misclassifying or causing it to misclassify inputs, then it's really actually simple. I wouldn't say it's poorly conditioned. I mean, looking at this, and just to going back to the logistic regression problem here. So this is not necessarily poorly conditioned, right? It has more to do with really the size. I can still fool this if the size of n is very large. So it has more to do with dimension than it does with the condition of the neural network. And you have to remember that these are crafted in a very specific way. So when they're trained, both test samples and training samples, they do perturb them all sorts of ways, and you still see accurate classification. But when they're crafted in very specific ways, that's when things tend to go awry. And it has more to do with dimension than some sort of faulty feature in the network. I guess that's kind of one of the messages of this talk is that that's really where the way we should think about this, as opposed to the old way of thinking, which is what you're describing. Does that make sense? Good question. Any other questions before we move on? Yep.
So I don't know the your image classification, but
For the record, I don't either. So
we apply those techniques, and I was wondering. So we don't have necessarily. I work in hybrid sciences, and we have uncertainty rather than adversarial examples. And one of the ways we deal with it is we recently worked on relational inference rather than learning having loss function where you learn a parameter vector in this very high dimensional space, you learn a distribution. Has there been work done which helps solve this problem through learning distribution rather than point vectors?
So what I'll say is, so when it comes to catastrophic overfitting, so there's something similar to what you're describing there. Go to here. So at least three of the methods here, the way they get around catastrophic overfitting is by adding a little bit of noise, right? So in different ways. And the idea is by adding noise, you make it a little bit more robust. So we're not really learning a distribution, right? But what we're doing is during, like, to craft the defense, adding the noise during training. The idea is to train against this, when you're training, as opposed to training with that. And so what it does is it forces one of the ideas is to force the loss landscape to be a little flat. You don't have these steep valleys, right, in the loss landscape. So that's one of the running ideas. It's somewhat related to what you're describing, but it isn't exactly what you're saying. I hope does that answer your question?
Yeah, I would like. Is it something? The question is this is really cool because this is the inference you just had in one parameter vector. Whereas if you have a distribution you have to run, is that like the computational cost that can't be run afforded in cars because you can't run the same network thousands of times to basically input from the distribution? So maybe that might make robust.
I guess that the two things are synonymous. So whether you're working with a probability distribution, you're introducing robustness that way, or during training, you're introducing noise. I mean, ultimately, it's if the input has noise, the output is going to be something that takes that noise into it. It's probabilistic. The input is probabilistic, the output is probabilistic. So that's one way that they do it. Any other questions before I move on to the next part? Okay, so the next part really examines the question of how linear are neural networks. And here we use Koopman theory. So Koopman theory comes from dynamical systems where you have, in this case, I'm showing you a discrete dynamical system where the updates go through a nonlinear map. So these can be very complicated. So the idea in Koopman theory is to map the state space, so where you live, to a higher dimensional space in such a way that the evolution becomes linear in the observable space. Okay, so you map it to higher dimensional space, and there, instead of having to use a nonlinear map, we have a linear map that is time independent typically. Okay. And so if you think of like what's happening in the state space, you have your initial state, and it gets mapped to, you know, it's mapped to the next state and the next state through this nonlinear formula. In observable space, what I can do is I can take a shortcut all the way to the end by just taking that linear operator to the power k, and then multiplying it by the initial observable, and then mapping back, assuming that I can map this way and mapping back. So the challenge here is being able to find the proper embedding. So to get more intuition, I'm going to use two canonical examples to show you how this works. So this is one example of a dynamical system, nonlinear, because I have a squared term in the second equation. And so because I have, well, the first term is linear, and then I have something that is linear and quadratic, what this inspires is an embedding where I have three coordinates, one responsible for x1, one responsible for x2, and because I have x1 squared in the original model, I'm going to set the third coordinate to be equal to x1 squared. Now what happens is if I look at the derivatives of y1, y2, and y3, what I end up with is something like this, right? So, and this is going to be my Koopman operator, right? So y1 and y2, I get directly from the original dynamical system. Y3, if you look at y3, I'm just taking the derivative of x1 squared, so that's 2 x1 x1 dot, and x1 dot is equal to mu x1, so that's equal to the third coordinate. And you get closure. So I don't need any more dimensions. This is a very good embedding, and this is very useful if you're doing control. So if you're trying to solve a control problem, it's a lot easier if you're working with something that you can linearize, right, as opposed to working with the original. But it rarely really works. What you'll see more often than not is something like this. Okay, so this is a different dynamical system. This is the logistic map. Very simple, very similar to the last one. And in this case, you know, drawing inspiration from what we did before, you'd be kind of tempted to have your embedding take x and x squared as its coordinates. And then you want to find k that maps your coordinates at time k into the next time step. So for the first one, I get a linear equation, right? For the next one, what happens is I have to square the coordinates, and now I have something that corresponds to x3 and something that corresponds to x to the power 4. And so I have to add those to my coordinates. And so my original embedding is no good. And when I add something that would give me this term, I'm going to need more and more terms. So this thing just starts to run away from us, okay? And there is no finite dimensional representation, at least not using this coordinate transformation that allows me to do to come up with a Koopman operator, right? So this is infinite dimensional, and we don't want that. This tends to be the case. This is what you'll see in most cases. Okay. Right now, what we want to do is our function is not a dynamical system, but it's a neural network that has, we're thinking of a multi-layer perceptron. I'm going to stick to multi-layer perceptrons in this presentation. So you have linear, or actually affine layers, followed by ReLU layers, and so forth, right? So linear, nonlinear, linear, nonlinear, and so on. What we want to do is we want to learn a representation of this that takes the same input, maps it to a higher dimension, so that's that psi, that first psi, and then we hit it repeatedly with the same matrix, and then we go back to the original space, okay? So we apply this k times, or I can just train one single matrix that's k to the power k, little k. And here the training problem is I want to match the original network. I want to see what the original network is doing. Okay, so our labels come from what the original network does, and we want to see if we can kind of match this. And we did a quick exercise here just to kind of understand what this looks like, to get some insight into it. And here we're looking at a binary classification problem of the lotus root. So this is a little too sophisticated. So we want to learn is these boundaries. And this is a little too sophisticated for something like logistic regression or support vectors. But this is a cakewalk for a neural network. A neural network can easily learn something that would classify these points correctly, right? Okay, so, and then here's the result. So we trained it, and you get a model that learns the boundaries, the original model. And we trained the Koopman surrogate, and it also learns the boundaries quite accurately, okay? So it works. So you can actually train a model that does this. Now, the interesting thing is to try and observe what the dynamics look like. So what I'm going to show you, so each frame of this video that I'm going to start is basically what you see in observable space after we hit it with the Koopman matrix once. So each time I hit it with a Koopman matrix, you're getting a frame here. Okay, well, okay, so this is, we're just going through this observable space. It's warping and it's warping the points. And what we're looking at is the first three principal components of what's coming out of each layer, right? So not much is going on, but it gets very interesting if I hit each frame with the inverse map. So I go back to the state space to see what it's doing. And again, these are the top three principal components. And here you see a lot more going on. So it's taking the data, it's warping it in such a way as to separate the orange from the blue. And where, I'm going to pause it in a second. Oops. And ultimately, what happens is, almost there. I'll pause it here. So it succeeds at separating the orange from the blue. Now this problem I can separate with a hyperplane. So this is something you can solve with logistic regression. So it seems that what the neural network is learning is something that takes a complex classification problem, turns it into an easy one. Okay? And there's a whole body of literature on this related to this called neural collapse, if you've heard of it. Okay, so that was like a neat little exercise that we did. But really the punchline that we have, and this is something we did this past weekend, is we actually came up with an analytical embedding. So this is a theoretical result. What we found is that for any multi-layer perceptron, there is a finite dimensional embedding that scales linearly, and by linearly, the linear factor is actually very small, linearly in the maximal dimension of the original network. So the embedding is not very high dimensional relative to the original network, right? So what we're saying is so neural networks look more like the nice Koopman example that I showed you, which is the exception, not the rule, than it does the one that's not so nice. Okay. And what I want to do is walk you through, okay, this was supposed to pop up later, but I want to show you how we do it. So the embedding is quite simple. All we do is so the embedding is analytical. I take the vector X and I just pad it with an appropriate number of ones. We just add ones to it. And then we create these operators that represent the affine operators in the neural network, but again, padded in such a way that I get a square invertible matrix. Okay, that's the underlying idea. And now if you think of the ReLUs as it's going through these activation layers, a ReLU is just a binary mask, right? So and it depends on what it's taking in, but I can think of it as a binary mask. So it takes whatever's coming out of the linear layer, and it's sampling some of them and setting others to zero. If it's a ReLU, it's setting the negative ones to zero, and it's keeping the positive components. So it's like a sampling matrix or a binary mask. Okay, so that inspires another matrix that we define, which uses that binary mask, and we pad it with an identity matrix to make this a square matrix. And so that now I can look at that network as a series of these multiplications. The Koopman followed by the binary mask, Koopman binary mask, Koopman binary mask, and so forth. This is just looking at what I have there through a slightly different lens. But now what we do is we take these R's and we're trying to propagate them out to the left. And you can do that analytically, given that if K is invertible. And we design K to be invertible. So for the first one, to move R from R1 to move R1 to the other side of K2, it's just a simple calculation. And then for C2, and then to move that outside of K3, it's another simple calculation, and so on. And what you end up with is you have one operator here multiplied by a bunch of square matrix multiplications, and then we have our embedding, and that's just our Koopman matrix. So we do it by design. And any neural network, fits, or multi-layer perceptron fits within this framework. Okay, so that's kind of the result that we have right now. All right, so the last part, I'll go through this very quickly. This is what we do in inference time to clean images as they're coming in. And what we're using is error correcting codes. So an error correcting code is something that they use in communication theory. So let's say I'm trying to transmit a bit between a sender and a receiver through a channel that might be noisy. So there's, let's say, a 30% probability that a 0 that I'm trying to send you turns into a 1 through this noisy channel, and a 1 that I'm trying to send you turns into a 0. A way around that is for you and I to agree that I'll send it to you 3 times, and you do a majority vote. Now, if I send it to you 3 times, that majority vote, the probability that you get it wrong goes from 30% down to 3%. So that's the idea. And we do the same thing here. And except instead of using bits, I'm looking at graphs. And the reason I'm looking at graphs is they're very complicated. So if you can do reliable error correction with a graph, you can do it with an image. That's the idea. So that's why the focus was on graphs. And if you think of a graph, it's just the way to define it is an adjacency matrix. So it's just a matrix of zeros and ones that we want to transmit reliably. And the strategy is that the sender creates many copies of the graph. It goes through the channel. It might get adversarially perturbed, and then we reconstruct it by doing a majority vote. So that's the idea, and this tends to work. But the question that we were trying to answer is how many repetitions do you need for this in order for the reconstruction to be reliable for a graph. And this is I'll just give you the result. This is the bound that we determine. It's quite it's not a very conservative bound, but the nice thing is that it scales with the size of the network. The larger the network gets, the smaller the number of repetitions that we need, is the way to think of it. And then we tested it on graphs that were simulated, generated randomly. And these are I'm not going to show you all the results. Most of the results were pretty good. Again, our bound is very generous. This is a more pathological example of when there's a second error mode. So the adversarial perturbation we're doing is we're cutting out the vertices that have very high eigenvector centrality. Okay, so that's something that attacks the actual structure of the network. And it's very hard to reconstruct those kinds of edges. So the way we fix this is by increasing the sender assigned perturbation. So what the sender puts out there is something that we add noise to. And there for most of the graphs that we tested with, we were able to correct them, correct the graph entirely, get the original graph back. Okay, this is an exercise that I gave to my students. I showed them my paper, a probability and statistics course, and I asked them to use the same idea, run it on images that were adversarially perturbed. And not only did it correctly classify, and they would use 3 repetitions only. Not only did it correctly do it, but it also removed some of the noise that was in the original image. All right, so this is my last slide. And so here are the takeaways. So where are we going with this? What we want to do is, so tying everything together, we want to be able to adversarially train the Koopman surrogate. Now, we anticipate that that would work better because of the linearity of the Koopman surrogate. So I don't have to assume linearity, it's already there. So FGSM will work very well on the Koopman surrogate. So that's what we anticipate, and that's where we want to go next. The other thing we want to do is try to train low-rank surrogates. And this is what this does is it reduces the dimension of the problem. It also gives me alternative versions of this Koopman surrogate. So one thing we did some initial exercises. So what I want to do is use these Koopman surrogates for error correction, right? We don't have senders and receivers in autonomous vehicle classifiers. So we did some tests. We took a classifier that classifies handwritten digits, and we did a Koopman surrogate of it, and we attacked them. So we attacked the so this is so we took the original network, we crafted an attack on the original network, and then we tested how that affects the Koopman surrogate and vice versa. And what we observed is that they're robust to each other's attacks. So that gives us hope that we can use this in an error correction framework. The other thing we've observed, and this is very inconclusive at this point, but we did test using so these are kind of like the figures I was showing you early on with the catastrophic overfitting. We tested so we trained with FGSM, these the Koopman surrogates, and then we attacked with PGD and to see how, and we used those for error correction. And it seems to work, at least for that very small example, but this has yet to be verified on larger networks. But this is where we're going. Okay? And with that, I will end my presentation. Thank you all for listening. Be happy to take any questions.
The graph. Sender perturbs graph. And here's what function was for the perturbations of the sender. How do you decide what?
We just did, okay, that's a great question. So these were just random. So the idea is that these perturbations have to be small, right? We don't want to perturb them too much because if you perturb them a lot, you're gonna have to undo the perturbation that you added, right? So you don't want the perturbation to be large. So you want it to be small enough to conceal the structure of the graph, but at the same time, small enough that you don't really need a lot of repetitions to reconstruct the graph after the adversary perturbs it. Now, in principle, it should depend on the structure of the graph. So here we're using what is, I forgot what they're called, but they're random graphs, just your garden variety random graph. And so you can use just additive noise, an IID vector of additive noise, right? That's all you need. If you're working with a scale-free network, something that exhibits power laws as you increase the graph size, that will not work. Actually, the perturbation, the sender assigned perturbation does more damage than good in that case. And you'd have to design it in such a way that conceals the structure in a way that the receiver knows how to undo it, okay? But that's not something we looked into, but it would be of interest to say, so this is published in the physics journal, so network scientists, physicists would be interested in that kind of a result. Yeah.
Does this Koopman representation of neural network gives us any advantage of computation over the neural network itself? I mean, does this matrix have nice properties?
No, not the ones that we have been working with so far. It has nice properties from the perspective of what you wind up with, but not computational. So what we're doing is we're saying, training is training. Let that take forever. We don't care. As long as we get something that matches the original network, and then we want to pick that apart in various ways. But it doesn't give us any computational advantages. It might, well, no, I won't even. I was going to say there's a low rank version of this where you say, instead of training K, you train A times B, where you have a wide matrix multiplied by a tall matrix. So you have far fewer parameters that you want to multiply. But really, we're trading off dimension for complexity, right? So we're getting around nonlinearity by looking at this in a higher dimensional space.
And is this like a full rank matrix or?
Yes, yeah. I mean, it can, so all of these are designed to be invertible. They're all the same size, and if you multiply a bunch of invertible matrices by each other, you end up with an invertible matrix. So yeah, it's full rank. It's another very good question that has a lot of implications. Again, I'll thank you all for listening. And thank you for letting me come here and present. Let me see, there's questions in the Q&A. Oh, wait.
Can you hear me?
Yes, I can hear you.
Okay, great. We do have two questions in the chat, so I can read them out to you.
Okay.
The first one, which is, how is the learning Koopman operator directly from observed data different than learning it via the DNN?
Good question. The difference is we're trying to understand what the original neural network does, as opposed to trying to tune something to predict accurately. So you can do it with the original data, but we chose not to because we're really trying to build a surrogate to the original model. That's but we might try that at some point.
Great. And then the second one is, how does this method work with the original video, Jeep driving into a valley, and then parentheses, no stop sign or traffic light involved?
Well, the Jeep driving into a valley was an actual hack of the hardware, so this doesn't address that problem. No stop sign or traffic light involved. We have yet to test that. So I'm assuming by that you mean back doors. We have yet to test that.
Great, those are our two online questions.